simply the simplest short quadruple proof ever of Fermat's last theorem. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. If we take the Fermat triple z to the n equals y to the n plus x to the n and restate it in its two different forms as 1 z to the n minus y to the n equals x to the n, and 2 z to the n minus x to the n equals y to the n, then dividing 1 by 2 we have z to the n minus y to the n all divided by z to the n minus x to the n is equal to x to the n divided by y to the n. Multiply both sides by the reciprocal of the right hand side to give z to the n minus y to the n all times y to the n all divided by z to the n minus x to the n all times x to the n is equal to x to the n times y to the n all divided by y to the n times x to the n equals 1. Replace the right hand side with 1 and rearrange the left hand side by moving the denominator to replace the 1 to give a z to the n minus y to the n all times y to the n is equal to a z to the n minus x to the n all times x to the n, so that on multiplying out and further rearrangement we have zy to the power n minus x squared to the power n is equal to zx to the power n minus x squared to the power n. Fully restate 1 as the quadruple equation C zy to the n is equal y squared to the n plus zx to the n minus x squared to the n. Quadruples are only known to exist for the first, second, third and fourth powers, but only first and second powers are of the form of equation C and are formed by all and every identity a plus b equals c, and by inputting a primitive Pythagorean triple into a plus b all squared is equal to a squared plus 2ab plus b squared. This is just Euclid's Elements, Book 2, Proposition 4. When, as has previously been demonstrated, we get a unique trio of related Fermat-Bateman quadruples. This demonstrates conclusively an all-integer Fermat triple to be an absurdity, QED. As well as equation C, we also get two more equations, A and B. Since the Fermat-Bateman quadruples are a derivative of a plus b all squared, then there exists a trio of Fermat-Bateman quadruples for every binary partition of the number given by a plus b, as the two following numeric examples given as a 3x3 matrix demonstrate, noting that the exponent must be n equals 1. For 11 equals 10 plus 1, therefore z equals 11, y equals 10, x equals 1. Therefore z squared to the power n is equal to 121. zy to the power n is equal to 110. Y squared to the power n equals 100. Zx to the power n equals 11. Yx to the power n equals 10. X squared to the power n equals 1. Substituting the numbers into the equations, we get the numeric Fermat-Bateman quadruples as shown. Repeating, for z equals 2n plus 1, y equals n plus 1, x equals n, we get another three numeric Fermat-Bateman quadruples as shown. Notice that when we use the binary partition n plus 1 and n, we will always get an adjacent pair of triangular numbers, the difference of the squares of which will always be the cube of the difference of the two triangular numbers. Corollary 1. Since every odd integer 2n plus 1 is the sum of its binary parts, then there are n sets of Fermat-Bateman quadruples associated with every odd integer. 2. This is in agreement with the identity a plus b all squared, from which the Fermat-Bateman quadruples can be derived, and vice versa. 3. The three Fermat-Bateman quadruples simply rearranged to give three difference of squares equations, a squared minus b squared. 4. Every integer x to the n, y to the n and z to the n, no matter how large, can be obtained by the difference of squares equation, a squared minus b squared, for a minus b equals 1 and a and b incrementing by a half at each step, and starting 1 squared minus 0 squared equals 1, 1 and a half squared minus a half squared equals 2, 2 squared minus 1 squared equals 3, 2 and a half squared minus 1 and a half squared equals 4, 3 squared minus 2 squared equals 5, and so ad infinitum. 5. The difference of squares equation, a squared minus b squared equals x, is just the Pythagoras equation, a squared minus b squared plus the square root of x squared, where any or all of the three terms may be or may not be rational or irrational. 6. So all in all, it has been demonstrated and substantiated that an all-integer Fermat triple to an integer power of 3 or more is, to say the least, just an absurdity. QED. That's all, folks.